Today we are starting on a new chapter. We're starting on chapter 6, which we will not cover the entire chapter, just the first 3 sections of it. But this chapter is all about a new concept called eigenvalues. So what is an eigenvalue? Well, the idea is, remember, a matrix can be thought of as a linear transformation, or you can think of it as a function that takes vectors and gives you new vectors. And if we start with a square matrix, then those vectors, the vector that we start with and the vector that we end up with, have the same size. They're in the same Rn. So it's natural to think, well, what if we get the same vector back that we put into it? Well, that usually won't happen, though it can. But what happens more often is the vector that we end up with is a multiple of the vector that we started with. In other words, if we take our matrix and we multiply it to this vector x, we want to get back a multiple of the x that we started with. And it's pretty standard to use a lambda. This is a Greek letter lambda for this kind of a situation. It's it may not be the most natural for new students, but it is a pretty standardized notation, not only for mathematicians but other people that use these eigenvalues throughout, say, physics and stuff like that. But we are going to call this lambda an eigenvalue, or as the book says, a characteristic value of A. Now, the term eigenvalue, eigen comes from a a German word meaning characteristic. So we're just using some foreign language here. But I prefer the word eigenvalue because it's a little bit more unique. Characteristic value feels too generic in my view. So we'll stick with eigenvalue, and we will say that it's an eigenvalue if there's an x that makes this true. But since putting 0 in here would make this true for any number lambda, then we'll specify that we need to have a non-zero vector x that makes that true. If any x that does make that true is going to be called an eigenvector that belongs to or corresponds to the eigenvalue lambda. But this non-zero vector here is very important. Now, how do we find these eigenvalues? If we start with a matrix A, how would we find them? Well, let's take the equation that we started with, and we'll kind of turn it around. So first of all, we want to bring the lambda x over to the other side. And as you probably actually might notice already, it feels like we should be able to factor x out. Unfortunately, we can't do that right away because over here we're just taking a number times x. Over here we're taking a matrix times x. Those are very different types of products. So in order to kind of factor out the x, we have to turn this side into a matrix product. Well, we can just replace x with I times x, I being the identity matrix. So we have ax minus lambda times the identity matrix times x. Now that is actually a matrix product, and we can go ahead and factor. So we have a minus lambda times I x equals 0. So lambda is an eigenvalue of A if and only if there is a non-zero solution, a non-zero vector that makes this true. Now, how do we know if that's going to happen? Well, this has a few different characterizations. First of all, any x here is going to be in the null space of this difference, a minus lambda I. So remember our null space. And what we're saying here is that the null space is not just the 0 vector. That also means that because because the determinant, or let me start over there. Remember that a matrix is non-singular if and only if, when you take the product of that matrix times any vector, any non-zero vector, you never get 0 out. Or in other words, A is non-singular if A times x equals 0 means x equals 0. So if there's anything that's not 0 that makes it equal 0, that means this matrix here can't be non-singular. It has to be singular. Or in other words, the determinant of that matrix equals 0, because that's supposed to be a singular matrix. So these are very important ideas and very important ways of actually finding these eigenvalues. We look for lambdas that makes the determinant of this difference equal to 0. So that's what we're going to do here. The equation determinant of A minus lambda I equaling 0, that's going to be called the characteristic equation. We don't call it the eigenequation. We just use characteristic at this point. We call it the characteristic equation for the matrix A. And because when we actually expand that determinant out, it always turns into a polynomial. In fact, if A is an n by n matrix, it'll always be a polynomial of degree n. We are going to call that the characteristic polynomial of the matrix. And there's actually things you can do with the polynomial itself, but most of what we're going to be doing is trying to set that polynomial equal to 0 and find the solutions for lambda. It's a polynomial in lambda. And those roots are the eigenvalues of A. The subspace, the null space of this A minus lambda I, because it consists of all the eigenvectors corresponding to the eigenvalue lambda, assuming that lambda is an eigenvalue, that this is not just the 0 vector, we're going to call that the eigenspace corresponding to lambda. And then, well, that leads to other conditions for what it means for something to be an eigenvalue. An eigenvalue is something where this equation has a non-trivial solution, meaning it has a solution other than x equals 0. It means that our null space is not just the 0 vector. It means that A minus lambda I is a singular matrix, and it means that the determinant of that matrix is 0. Those are all equivalent definitions for lambda to be an eigenvalue. And we're going to make use of those different conditions in order to actually find those eigenvalues and to work with them. Now, of course, you're going to want to pay close attention to the examples video in order to see the process for doing all of this. I'm not going to do an example right now, but I do want to note here that, remember, because we're dealing with a polynomial here, we're dealing with our characteristic polynomial lambda, or characteristic polynomial p for A, and we're trying to solve for lambda. Because we have a polynomial equals 0, we know that we have solutions. We have what we call the fundamental theorem of algebra that says any polynomial, any degree in polynomial where n is bigger than 0, a 0-degree polynomial is just a constant. That doesn't really have a solution. But any other polynomial will have a root. There are going to be, in fact, for degree n polynomials, in a certain sense, if we count what we call multiplicities, it's going to have exactly n roots. But we do have a slight issue. It has n roots if we involve complex numbers. So here we cannot truly get away from discussing some complex numbers. In fact, complex numbers will be very useful for us in the next section when we actually apply this to differential equations, which we're going to get into a little bit differential equations. If you haven't seen differential equations yet, we won't really get too deep into it, but we will discuss some of it as an application of this concept. But what do we have to do if we're dealing with complex numbers as our potential eigenvalues? Well, we actually do need to think about matrices themselves that have complex numbers in them. So we might have something like, I don't know, a 2 by 2 matrix where A is 1 plus I. We might have just a real number in there, maybe two real numbers, and then something like that. And we could ask, well, what could we do with this kind of a thing? But really, we're not doing anything very different with it. It's still just an array with numbers in it. They just happen to be complex numbers now. The main thing that we might want to actually worry about is remember that when we have, say, if we have, say, z is equal to 1 plus I, we have an idea of the conjugate of z, where we change the sign of the number in front of the I. So z bar would be 1 minus I. We can do the same thing with matrices. This just means that we're going to take all the entries in A and we're going to take their conjugate the same way. So this 1 plus I will become a 1 minus I. The 2 plus I is going to be a 2 minus I. And of course, it doesn't change the 3 or the 2 because there's no I part in there. Those are real numbers. And that means that if A and A bar are the same, then A only consists of real numbers. So we say A is a real matrix. Just like if Z equals Z bar, then Z is a real number. But the important thing here is that if we do have a real matrix and we have an eigenvalue corresponding to that, or an eigenvalue of that real matrix, then those eigenvalues come in these conjugate pairs. That's actually a result from algebra, our fundamental theorem of algebra and all that kind of stuff. If we have a polynomial with real coefficients, then the solutions, the roots of that polynomial, are always in conjugate pairs. And in fact, if, say, x corresponds to some complex eigenvalue, so ax equals lambda x, if we take the conjugate of that, if A is a real matrix, we can break that apart and say that, well, let me put it this way. Over here, this is actually A bar x bar, and if A is a real matrix, this is just A times x bar. So we actually get A times x bar is equal to lambda bar times x bar. So if lambda is an eigenvalue, a complex eigenvalue of a real matrix, then so is lambda bar, and the eigenvectors of lambda bar are just the conjugates of the eigenvectors of lambda. So just keep that in mind. We won't be doing too much with that, and in fact, we won't even be seeing any of that in our examples, but we will be using a few examples of that in the next section, because it actually does have a very important application to those kind of problems that we really can't ignore, because it actually has a real world consequence to those complex eigenvalues. So just warning you. That's all you really can say right now. Another thing that we can do is we can imagine what happens if we kind of pull apart this characteristic polynomial. So we have our characteristic polynomial like this. If we write this whole thing out, so let's say that A consists of A11, A12, and so on and so forth. Remember, we're subtracting lambda times I. What that means is that we're subtracting lambda from each of our diagonal elements. But everything else actually stays the same. It's always fun having to write all these big matrices out. But it turns out if you actually take this determinant and work with it a lot, there are two things that will happen. First of all, it's one thing that's really easy to see is if we plug in 0 into here. If we plug 0 into this characteristic polynomial, it's going to make a minus 0. It's just going to be the determinant of a. That means that the determinant of a is literally just the constant term of this polynomial. But it also turns out, if we do all this multiplication and work it all out, then because the lambdas, the eigenvalues are the solutions to this, the roots of this polynomial, we can actually write this polynomial in terms of those roots. We can actually write those as lambda minus lambda 1, where lambda 1 is our first eigenvalue, then lambda minus lambda 2, where lambda 2 is our second eigenvalue, and so on and so forth. We have n of those, and we can write it like this. Now we do want to be a little bit careful here. Technically, because we put it as minus lambda I, we actually have a lot of negatives. We're going to get a negative 1 to the n. It's usually a little bit better to go ahead and actually put this in the opposite order. Lambda 1 minus lambda times lambda 2 minus lambda, and so on and so forth. So the characteristic equation can always be written in this form. If we were to multiply this out, what would be the constant term? Well, the constant term would be taking each of the lambdas, the lambda 1, lambda 2, lambda n, and multiplying all those together without any of just the plain lambdas. In other words, the product of all of our lambdas, or all of our eigenvalues, is the same as the determinant of our matrix. And that's actually one way to think of the determinant. It is the product of the eigenvalues. In fact, there are treatments of linear algebra where they actually define the determinant to be just the product of the eigenvalues and treat eigenvalues as being more fundamental than the determinant itself. But that gets a little bit more on the more abstract side. So that's why we define it the way that we do. In fact, that kind of explains why the determinant is so important. The eigenvalues have a very simple definition. The determinant didn't have a very simple definition. It had a very complicated definition. But those simple definitions turn into something that is very simple in terms of those eigenvalues. Keep in mind here, these lambdas, the lambda i's might be repeated roots, so you have to take that into account when you form this product. But it is still important that we have that. Another thing that we can actually see, and this would actually take a lot of actual computing to really break this apart and show it, but I'll just have you take my word for it for now. If we look at the coefficient, not of lambda to the n, lambda to the n will have the coefficient of negative 1 to the n. That's always going to be our first term. But the second term is always going to look like first of all, we have this negative 1 to the n minus 1. I'm not going to worry about that part. It's always going to have two different forms. Well, one coming from the original determinant. It looks something like the sum of all the AIIs. So this is A11 plus A22 all the way through ANN. Or, if we were to look at this formula here, we get a very similar result. We'll still have that negative 1 to the n minus 1, but we're going to have the sum of all the lambdas. So I have this. So the sum of all the eigenvalues. And of course, those have to be the same thing because we're working with the same polynomial. So the sum of all the eigenvalues is actually the sum of all the diagonal elements of A. That's actually an easy way of looking at it. And that shows you that the sum of all the diagonal elements has kind of a meaning to it. It's not just some random thing that we could have picked out of the matrix. And so we actually give it a name. We call it the trace of the matrix, which we put as TR of A. And the determinant and the trace are very frequently thought of as kind of a pair of two things, but it was a little bit more tricky back when we were talking about the determinant in the first place to show why the trace had really any meaning to it. I mean, it has a very nice, simple definition. It's just the sum of the diagonal elements of our matrix. But why does that have any use to it? Well, it has use because it's the sum of the eigenvalues. And that means that it actually does have some consequences to being able to talk about the trace of it. We're not going to get into any of the actual applications of the trace here, but if you ever heard about the trace of a matrix, that's why it's kind of so important. One final thing that we're going to talk about in this video is that if we have two similar matrices, so remember B being similar to A means that there is a non-singular S, where B is equal to S inverse AS. If these two matrices are similar, then they have the same characteristic polynomial and the same eigenvalues. So here, remember, this is one thing that you had to do in your homework previously. We saw that we can pull this apart, and the determinant of S inverse is the 1 over the determinant of S, and so they cancel each other out. So their determinants are the same, but not only that, if we look at B minus lambda I, this is the same thing as S inverse times A minus lambda I. I think we actually did a problem, maybe in the example video or on your homework, where you actually showed that. And so what does that mean? That means the determinant of B minus lambda I, which is the characteristic polynomial of B, is the same thing as the determinant of A minus lambda I. So the characteristic polynomial of A. So they definitely have the same characteristic polynomial, which that means they'll have the same roots, and so they have the same eigenvalues. So why did we actually talk about similar matrices in the first place? Well, we talked about them because that really means that A and B they're actually just the same linear transformation in a sense, just maybe under a different basis. So that's why we actually mentioned these in the first place. If we change the basis, then we can change one matrix into something that's similar to it. And this is saying that, well, if you change the basis and think of the linear transformation changing to another matrix representation, then you actually don't change your eigenvalues. So in fact, what this really means is that the eigenvalues are a property of the matrix as a linear transformation and less of it as a matrix. Now, that is not really true of the eigenvectors. The eigenvectors of corresponding to lambda for b and for a can be a little bit different. There's actually an exercise about that. Yeah, exercise 26. So this is one that you're going to have to show is that if b is similar to a and x is an eigenvector of b belonging to this lambda, then not x is it's not that x will be an eigenvector of a corresponding to lambda, but s times x. So I'm going to leave that for you to actually work on, and it's not really that complicated. But if you have any questions about it, you can come ask me in my office hours. But I'm going to go ahead and leave it there. We're going to actually work out how you find these eigenvalues in the examples video. I just wanted to go through all the definitions right now and get an idea of how we can actually think about these things. But no real examples in this video. I'll see you guys in the next one.